June 10th, let me talk about some Fibonacci surprises. This actually connects with something I did last time I spoke at the Sigma, where I gave a talk on 5 principles on how to think like a high school math genius. And one of my principles was the power of a picture, really visualize, use pictures to your advantage. And this talk is some Fibonacci surprises about coming from a particular picture that I found particularly powerful and particularly exciting. I haven't actually done this with kids yet, but I'm actually itching to do this with one of my classes next semester. So let me give a sense of what's going on here. So it's obviously about the Fibonacci numbers, which we know very well. They rise in all sorts of places in nature and in mathematics, and they're very exciting. So the first Fibonacci number is 1, second Fibonacci number is 1, third is 2, fifth is 5, 12th is 144. And one particular context I want to look at these guys is from this classic puzzle. Because I talk to people, not many people seem to notice this puzzle. I think it's very, very standard. But imagine a honeycomb structure. 2 rows of hexagonal cells. And I'm a bee starting the cell labeled S to start, and I would love to walk to the end cell labeled E. And my rules of motion are such that I must walk from one cell to the adjacent cell, always moving rightwards to some degree. It means I can take diagonal down steps, diagonal up steps to the adjacent cell, or I can take horizontal steps, either horizontal steps at the high level or horizontal steps at the low level. The question is, how many paths are there from start to end in this particular picture? Alright, very classic puzzle with Fibonacci numbers, and we're going to just go through the answer very quickly. So, like all problems, don't start with the most complicated case. Let me go back to small levels and see if we can just get a feel of what's going on. If you think about it for a moment, if I'm going to take down, up, or horizontal steps, there's only one way to get to this cell, take a down step. And the next step in this case is this guy. There's 2 ways to get to this cell, either go directly across or down and up. And a little bit of playing, you'll see there's 3 ways to get to this cell. And then after a while you get bored and realize things have got complicated, maybe we need a more sophisticated way of counting these things. So let's look at this second cell on the top row. You say to yourself, how can I get here? Or 2 choices. Either get yourself to the cell directly to the left, there's 2 ways to do that, and then step across. Or get yourself to the cell below, there's 3 ways to get there, and step upwards. So this gives me a total of 2 plus 3 possible ways to get to that cell, must be 5. And in fact that constructs very similarly, you can go all the way through. This 8 must be either get directly to the left, 1 of 3 ways. Yourself from that, naming yourself at the top, 5 ways, the answer must be 3 plus 5, 8. So that's the construct. Every cell has answer being the sum of the 2 previous answers, hence the Fibonacci numbers. So this is the picture I like to play with, where the number of paths to any particular cell is the Fibonacci number. And we'll just deem there's only one way to get from start to start, hence we'll make that F1. So we see to get any number of paths on the top row, there's an odd index Fibonacci number. Number of paths getting to a bottom cell on the bottom row is an even index Fibonacci number. And the game I want to play with that, which I think is just perfect for kids, is let's interpret paths in different ways. And I'll do some classic things first. Number 1. Just to help me out, rather than keep drawing hexagonal cells, let me just draw a zigzag line. So these dots represent the cells. And these steps can be down steps and up steps. And of course, I can still do horizontal steps. I didn't draw the horizontal steps here. But I need to think of my picture as a zigzag line of n dotted steps. Now, if I'm trying to keep track of counting, there are actually n spaces, n line segments here. That's really going to be n plus 1 cells. My index is off by 1, but I'm not going to fuss about that too much. But you can see straight away, for example, if I have a path that goes through this honeycomb, I might actually follow one of the dotted line segments, that'll be a diagonal step, or I might go a horizontal segment, which actually skips 2 diagonal steps. But right there I can see that I've already got a partition of my number n plus 1 into 1s and 2s. There's an ordered partition using the symbols 1 and 2. And conversely, any ordered partition using 1s and 2s is going to correspond to a path. So right there I can see from the power of a picture that the number of ordered partitions of a number using 1s and 2s must be a Fibonacci number. That's a classic result, very easy to prove other ways, but there it is coming from the type of game I want to play. There's another interpretation. Given a path through this honeycomb, consider each diagonal step to be a break. And all I've done is like tease this line up, so I made my dots into a linear row, and there are all the breaks. So basically I've taken 12 dots and put breaks in. Well, you can see what I'm doing right now. But there's one thing to note. Between any 2 breaks, here's an up step followed by a down step. I'm actually dealing with an odd number of dots. I'm on the top row and I end on the top row before I reach my next break. So actually between these partitions, there's going to be an odd number of dots. In fact, any partition into an odd number of pieces is going to correspond to a path, and vice versa. So I actually I can see right away by some results. That's the result. That the number of ordered partitions of the number n into odd parts, again, it must be a Fibonacci number. Right, nothing new there. Kind of powerful. So let's get wild. So here's one symbol, and I'm going to place parentheses around it. Not very exciting. I either do it or don't do it. Two ways, two choices. If I give myself two symbols, now it's many ways I put parentheses around two symbols, and I'll avoid nested parentheses. Essentially, just there are 5 ways to do it. Things get a bit tedious, but for 3 symbols, there are 5 ways, there are 13 ways to put parentheses around a set of 3 symbols. And then I'm starting to wonder something, because what do you notice about the numbers there? They're Fibonacci, but they're not in order. I skipped over the number 3 to 3, 5, 8, 13. So my question is, if I kept playing this game, is it every second Fibonacci number? For sure. Was this just coincidence? Of course not. Yes, it is every second Fibonacci number. And here's why. Here's why. Just the power of the picture. So when you consider paths that end on some upper dot, and the same as n dots that are happening on the bottom, all I'm going to do is interpret my diagonal steps as parentheses. But you see right there, if every down step's a left parenthesis and a right, up step's a right parenthesis, all it does is put parentheses around the bottom dots. And vice versa. If I give you a set of parentheses, it's going to correspond to a path. So the number of paths matches precisely the number of ways to put parentheses around things, hence it must be a Fibonacci number all the time. And it must be every second Fibonacci number, because we're talking about paths from the top level. So these are the Fibonacci numbers with an odd index, the ones counting powers from the top level. Alright, let's keep going. So I'm particularly fond of the number 1, and I like to write my numbers 1 with either a red pen or a black pen. And if I'm going to do that game, there's now 2 ways to partition the number 2. I've got 2 choices of the type of 1 I'd like to use. I can just write 2 itself, I can write red 1 plus black 1, or black 1 plus red 1, and so on. So there's 5 partitions of the number 2 using 2 different types of 1. If I look for the partitions of number 3, there's 13 partitions of the number 3 using 2 different types of 1. If we go back up a notch, there are 2 partitions of the number 1 with 2 different types of 1. And what do we notice? Is it every second Fibonacci number if I played this game? Well, of course, yes. Can we just see it with a picture? Yes. So I look at this path. Again, I'm going to consider paths that end on a particular top cell. So I'm sticking on the top cell, that's every odd index Fibonacci number. And here's a particular path that just drew at random. And I think to myself, okay, look at the spaces between the top cells that are touched. Sometimes these long runs before I go between 2 top cells, so a run of 3. But for the ones that are adjacent, there's actually 2 ways to do a single step across. Either like a down one, or I could do a horizontal step, just like an up one, I call it. So right there, I can see a partition of the number, whatever number I'm in right now, using 2 different types of 1. And vice versa, any such partition corresponds to a path. So I must be able to resolve that all the ordered partitions of the number n using 2 different types of 1 just must be a Fibonacci number. And every second Fibonacci number. Fabulous. Thank you, Sam. Inspire this one. Here's something totally crazy. Take your favorite number, mine is 3 for the moment. Look at all the ways to partition number 3. You think it's 3 itself, or 1 plus 2, or 2 plus 1, or 1 plus 1 plus 1. Take each partition and multiply the terms of that partition, and then sum the products. If I do that for number 3, the sum of the products turns out to be 8. So number 4, here's all the partitions for number 4. Here all the terms multiplied together, their product sums to 21. 8, 21. Sounds familiar? So my question is this always Fibonacci? And the answer is, well, yes. I can see it. So here again, I'm going to look at paths, and I'm going to look at specific locations of the u-steps, the up steps. So for example, there's one possible schema for a path, and that's where its u-steps could be. And I'm going to ask, okay, how many paths have u-steps in that position? Well, obviously I'm going to need some down steps. I'm going to need some down step eventually in that section. I need a down step betwixt these two U's that starts at the top and ends at the bottom. There's going to be at least one down step in there. But each segment requires a down step. And if I require myself to end on the down position, I need a down step somewhere in there as well. I won't have two down steps. There won't be two down steps somewhere here, because if there were, there would be some U step in between them that I would have mentioned. Since I didn't, I know there's a single down step in each segment. Alright, well that's handy, so let me count how many ways I can insert my down steps. So in this particular example, you can see there's two possible locations for a down step, which would be in the first segment, 4 in the next segment, and so on. Now there are 12 possible downward steps, and what I've really got here is a partition of the number 12, and since I counted different possibilities by multiplication principle, I'm really going to multiply those numbers together. So what I've done is taken a partition of the number 12 and multiplied its terms together. Well, if I do this over all possible locations of U steps, it must, in the end, be counting the total number of paths that exist, going from that start to this end. So the sum of all such products simply must be the Fibonacci number, the 24th Fibonacci number in this case. Just playing with the picture. So here's something else that's a little wild. So I seem to be focusing on every second Fibonacci number, 1, 2, 5, 13, 34, and 89. They seem to have a strange property. If I write triangular arrays of these numbers, for example, here's the first 4 of them, thought about the first 3 of them, the first 2 of them, the first 1, I get a triangular array of those every second Fibonacci number. So I add up all those terms. Turns out this triangular number of terms adds up to 33. Well, I do say the first 3 partial sequences, they add up to 12. If I did the first 5 partial sequences and add them up, they add up to 88. Always one less than the Fibonacci number. Curious. So my question is always one less than the Fibonacci number? Why, yes. A little bit more involved. But let's consider paths that end on a particular top cell. So some paths say end there. There's clearly one path that never touches a bottom row cell. Great. Now let's go through and count all the ways paths can touch some dot on the lower level. So maybe a path just touches a single dot on the lower level, in which case I can see there's going to be n such paths. Which dot is it? N cells at the bottom. There's n possible paths that touch just one dot on the bottom. And let me now go to counting how many paths touch a span of k dots somewhere on the bottom. I'll draw a picture of 2, which is the next picture. But suppose there's some span dots that are going to be touched on the bottom. Maybe there's going to be some between those, and here's a wider section of dots on the bottom that are touched somewhere along my path. Let's say there's k dots, there's a span of k dots on the bottom. I know the rest of the diagram is going to be just other steps. It turns out I can easily see there are n minus k possible places for that span of k dots. And what I do now is fill in how many paths are possible in that span versus own little honeycomb puzzle, and I know that's a Fibonacci number of ways. So actually I can see now there's n minus k times this Fibonacci number of paths of that structure. So one path that never touches a dot at the bottom, n paths that touch a single dot at the bottom. Now I've got formulas for how many paths touch a span of 2 dots on the bottom, span of 3 dots on the bottom, and so on. If I add up all those counts, that deals with all possible paths. Therefore I know I must have a Fibonacci number. And this looks scary, but it really is an algebraic formulation that's counting these up. N minus k times Fibonacci number. And believe it or not, that is the algebraic formulation that triangular array I was doing. It's actually heading by columns rather than by rows. And there it is. There is a purely visual proof of a nasty identity about every second Fibonacci number. I don't know if I've ever seen that actually. I don't know if it's around. But here's what's exciting to me to do this with kids. Kids are much, much cleverer than me. They love seeing patterns, they love playing with ideas in wild and crazy ways I would never think of. Now obviously I've been thinking about this, but I'm each to do this with kids and let them create their own weird and wild interpretations, and they will. If I want to really push this, I can make this a research project, is take your favorite identity and see if you can prove it via paths. So I was just mucking around. Actually, I kind of really like this. This is a well-known fact about the Fibonacci numbers, that A is a factor of n, and the 8th Fibonacci number turns out to be a factor of the nth Fibonacci number, which to me is wild, as Fibonacci numbers are additive in structure, It's a nice multiplicative property. So I wonder if I could prove that by the path method. And the answer is yes, I could, clever me. But now I want to go further. I personally have never seen a formula for the quotient. What is f of n divided by f of a in this case? As opposed to the formula for the quotient. Turns out yes. So I go further. What if a doesn't divide into n? What if there's some sort of remainder involved? Can you work out what the remainder is going to be of this particular division problem? And the answer is all by paths, yes. Not pretty. And I'm being a bit mean here. I'm not going to show you the picture of this, because the picture is actually fairly straightforward. I love it. But I've never seen this. Here it is. If a divides into n with quotient q and remainder r, then f of n is divided by f of a to some degree. Here's what the form of the quotient looks like. And here's what the remainder is going to be like, get to be divided by f of a. And what I love about this, it actually does imply the previous result. If a is a factor of n, then its remainder r is 0. And I see the remainder is going to have f of 0 here, and I didn't find at the beginning of the lecture the standard call f of 0 to be 0. So that tells me there's a perfect division going on, and there's a form of the quotient. So actually, take your favorite Fibonacci identity, and I bet you bottom dollar you could prove it by playing with paths. The pure visual interplay of the mechanics and the mathematics of the visuals. And I know I've thrown a lot of stuff your way, and in past years I've been spending hours at the photocopy for a conference and bringing photocopies for the real. I didn't print out this, but I have everything I've done written up. So it's a little personal plug here. So on my personal website, jameshannon.com, I have an essay which goes through 13 interpretations of I've just come up myself, and extensions, different ways to push it. And all the proofs, everything I've done here, all written up. And if you go to my site, there's various tabs. You can look under Think Cool Math to see this paper written up. It's the very first item on that list. So I want you to go and look at that. But I love the power of a picture. I just say, if you're a visual thinker, you've got the power of that light under your belt. So go for it. Thank you.